Hello everyone, welcome to Analog Electronic Circuits, lecture number 16, part number 1. So today we are going to analyze a common source, common emitter, RC couple cascade amplifier. So here is the circuit diagram given. Over here, as you can see, the first stage is my common source amplifier consisting of transistor M1 and channel MOSFET, biasing resistors R1 and R2, drain resistance RD, and we have a source resistance RS. We have a bypass capacitor CS, input coupling capacitor CC1, and output coupling capacitor CC2. Now the output of first stage is fed to the input of the second stage. And second stage over here is a common emitter, single stage common emitter amplifier, right? So over here, R3 and R4 are the biasing resistors, RC and RE are the collector and the emitter resistance, and your CC3 is my output coupling capacitor, and CE is my bypass capacitor. Over here, the input source Vs, which is AC, has an internal resistance R sig. So that is also considered. And at the output, we have a load resistance RL connected. It's a resistive load. Your VDD is the DC value, and Vs, which is a small signal AC, is amplified at the output. So V out is also a AC quantity. Now, let us bifurcate this into the source, first stage, second stage, and the load. So basically, why we are doing this, we want to estimate the input resistance Rn, output resistance R out, and the overall voltage gain AV for this amplifier, right? So let me just push this a little down. Yeah, and let me continue over here. So let me take a color green and let me identify which is the source over here for you all. So over here, this is my, to the left hand side of this region is my source. Then I have the first stage. This is my first stage. From year to year, and from year to year I have my second stage, and finally over here we have the load. Okay, this is my load. So amplifier is connected to the source. We have the first stage in the form of common source amplifier, second stage in the form of common emitter amplifier, and the load in the form of a resistive load RL. Now let us start with the analysis to estimate the Rin, R out, and AV. For that, we have to draw the mid-frequency small signal equivalent circuit. So let us start, and let me write it down over here that we have to draw mid-frequency small signal equivalent circuit for this cascade amplifier. So for mid-frequency small signal equivalent circuit, there are certain conditions. So at mid-frequency, we consider all the capacitors to behave as a short circuit, right? So these conditions will write over here. So here we'll write, first of all, short circuit, all connected capacitors. Short circuit, all connected capacitors. So let us have a look what are the connected capacitors. CC1, CC2, CS, CE, CC3. These are all connected capacitors which we have to short circuit. So we'll write it down over here. CC1, comma, CC2, CC3, CE, and then we have CS. Okay, so all these capacitors will behave as a short circuit at mid frequency. Then we have to short circuit any DC sources. Okay, so we'll write, because it's a small signal model, it will represent only small variations in the quantities, that is either current or voltage. So short circuit DC source. So what is a DC source in the circuit? So DC source in the circuit is VDD. So VDD will be short circuited for small signal analysis. for finding out the R in, R out, and AV. So short circuit DC source bracket VDD, right? And also we have to replace, now this I'm not writing, I'm just saying we have to replace M1 with a small signal model. It's a MOSFET, we replace it by a small signal model. And Q1, which is a BJT, will also replace it by a small signal hybrid pi model, right? So let us begin our analysis. Before going there, let me mark the terminals over here. So this is my gate terminal, drain, and source. Over here I have a base, collector, and emitter. Okay, so it's very, very important. That will help you to draw the mid frequency equivalent circuit without any problem. So let us first draw the small signal model for M1 and Q1, right? So I will require some space over here. Yeah, so let me first draw the small signal model for the MOSFET. So for the MOSFET we have gate, we have drain, and we have source. Let me mark the terminals over here. This is my gate, this is my drain terminal, and this is my source terminal, right? So what is connected between gate and source? For a MOSFET, gate and source is an open circuit, right? And we write over here voltage VGS. What is connected between drain and source? We have a current source, voltage dependent current source with the form of GM into VGS, right? So we will write GM1. The reason why we write GM1 is because we have another GM coming up for Q1 transistor. So we write over here GM1 into VGS. We'll also consider RO1 or RD1, we can say, right? That is the output resistance for this MOSFET. So we'll write over here RO1, right? So this is my small signal model for the MOSFET. Now comes the small signal model for the uh, the BJT. So BJT, we have base, we have collector, and we have emitter. So this is my base terminal, this is my emitter terminal, and that's my collector terminal. So in a small signal hybrid pi model for a BJT, between the base and the emitter, we have R pi. So I'll write over here R pi, and the voltage across it is V pi, right? So we can write over here plus minus V pi. And between the collector and the emitter, we have again a current source, voltage dependent current source, which will write it as GM2 into V pi. Okay, because already we have GM defined for the MOSFET model. Now also we'll consider the output resistance. So we call that as RO2. So here it is RO2. So now that we have drawn the small signal model for a BJT and a MOSFET, now it's time to connect the circuit, right? So we'll identify one by one which terminal where what will be connected. So let us start with the gate terminal. So at the gate terminal, we have resistor R1. This terminal will be connected to the ground. Resistor R1 and R2 will be in parallel, right? CC1 will be short circuited, and here we'll have R6 and VS in series. So let us go to the gate terminal. So at the gate terminal, we will have a resistor R6. Then we'll have R1 and R2 in parallel. So here it is R1 parallel to R2. And here we will have a voltage source VS connected. That's how the connection is. So here it is plus minus VS. This is my R6. And this is already marked as R1 parallel to R2. So gate side connection is completed. Now let's move on to the source terminal. To source terminal, we have a capacitor and RS in parallel. All the connected capacitors are short circuited. So a short in parallel with a resistance will be a short. So source terminal will be connected to the ground directly. So let us connect the source terminal to the ground. So here it is. Now let us see the connections for the drain terminal and the body terminal, how they are connected together, and the base terminal, sorry. Yeah. So between the drain and the base terminal, it's a directly connected a wire because CC2 will be a short circuit. Then we have RD going to the ground, resistor RD going to the ground. Then we have R3 and R4, which are in parallel because this terminal of R3 will be connected to the ground, right? So direct connection between drain and base, R3 parallel to R4, and then also RD also will be there, right? So first of all, let me connect them together. Drain terminal is connected to the base terminal. Then we have resistor RD going towards the ground. So here it is, resistor RD. Then we have resistor R3 parallel to R4. So here is the resistor R3 parallel to R4, right? And yeah, that's the connection between the drain and the base terminal. Now let us move on to the emitter terminal. So at the emitter terminal, again, we have a capacitor in parallel with RE resistance. So this capacitor will behave as a short. So emitter terminal will be directly connected to the ground. So let me connect the emitter terminal to the ground. So here it is, emitter terminal is easily connected to the ground. Now we have the collector terminal left. So let us go back to the circuit diagram. So from the collector terminal, we have a resistor RC connected to the ground because VDD is grounded. Then we have resistor RL also going to the ground. So RC and RL will be in parallel. So let me connect it over here. Resistor RC, and in parallel with we'll have a resistor RL. And across the resistor RL, we have a voltage, means in parallel again. So here we'll mark the voltage V out. Okay, and that will complete the small signal model, I mean the mid frequency small signal model for the given amplifier, cascade amplifier. So here it is, the entire circuit, right? Now looking at this mid frequency small signal equivalent circuit, we need to find input resistance, output resistance, and overall voltage gain. Now for finding the overall voltage gain, we'll mark one terminal over here, I mean one notation over here. So here we'll write V in. This voltage will write applied to the gate terminal will be V in. This is Vs. Now Vs and V in are differing by each are different, right? Because we have a RC resistance. If RC resistance was not present, it was zero. Our Vs and V in would have been same, right? Now also let me mark the output of the first stage. So after this resistor RD, I have an output of the first stage. So here we mark a voltage V1. This will be helpful to define the gain of the first stage and the second stage. So V1 is the output of the first stage and the input of the second stage. And yeah, rest all is fine. Correct? Now, let us first calculate the input resistance. So first we'll calculate Rn, and Rn is my input resistance. Now, when we analyze the cascade amplifier, what did we say? We have studied that your Rn, your input resistance, is equal to the input resistance of the first stage. So let me write it down. Rn will be equal to Rn of first stage. So we have to find the Rn value of the first stage. So let us do that. Let us concentrate on the first stage. So here is my first stage over here, right? Now let me use a green color. So let me call this as Ri. Resistance, I mean the input resistance looking into the V in, that is Ri, and input resistance looking into Vs is Rn. So we have to calculate Ri and Rn, right? So what will be Rn? Rn will be R sig plus Ri because they will be in series. So what is Ri? If I stand over here and look on the right hand side, I get R1 parallel to R2. This is an open circuit, right? So very easy it is to write here Ri. So what will be Ri? Let me write it down. Ri will be equal to R1 parallel to R2. And then finally, what will be Rn? Rn will be R6 plus Ri. So also let me write it down. Your Rn input resistance for this cascade amplifier will be Ri plus R sig. Yeah. So that's the formula for Ri and Rn. Right? In numericals, it is very, very useful. It's very critical to identify the correct formula. Now, what is next? Next, we have to calculate the output resistance. So let me write over here, second part, R out, which is output resistance. Okay. So to find the output resistance, what is the output resistance of a cascaded amplifier in a multi-stage or a cascade amplifier? Output resistance is equal to the output resistance of the last stage. Now over here, last stage is the second stage. Okay. So we have to go to the second stage and calculate R out. So let me go over here. Yeah. So where do I mark the output resistance over here? The output resistance will be seen from this terminal. So if you stand over here and look to the left hand side, what do you see? You see resistor RL in parallel with resistor RC in parallel with resistor RO2. Now, if you see further, we will see a current source. Now, current source will offer infinite impedance, right? So from here, it's an open circuit, correct? We don't go forward. So the R out will be RO2 parallel to RC parallel to RL. So let us write it down. So R out will be equal to RO2 parallel to RC parallel to RL. So this is my R out output resistance of this given cascaded amplifier, common source, common emitter amplifier. Right. Now, yeah. So now next thing we have to calculate is the voltage gain. So let me write down the formula for the voltage gain expression. Overall voltage gain, right? So we'll write voltage gain. It's a gain, that's why we denote it by A, and V stands for it is a voltage gain. Okay. Now let us continue our discussion. So the overall voltage gain of the given amplifier, right, will be given by output upon input. So what is the output over here? The output is V out and the input over here is Vs. So here I will write AV, which is the voltage gain, will be V out upon Vs, which can be written as, now the gain of the second stage will be given by V out upon V1, correct? And the gain of the first stage will be given by V1 upon V in. And there is a relation between V in and Vs, right? So we can rewrite this V out upon Vs as follows. It can be written as V out upon V1, then V1 upon V in, and V in upon Vs. Now, if you look carefully, the first stage over here, I mean the V out upon V1 is nothing but your second stage gain, AV2. And the second quantity over here is V1 upon V in is my first stage gain. And your V in upon Vs is because of the internal resistance of the source. Now, this quantity we have to calculate. Okay. So let us calculate this quantity now. V in upon Vs. So if you see over here, what is the relation between V in and Vs? It's a simple voltage divider, right? So V in will be equal to V in will be equal to Ri, which is R1 parallel to R2, divided by R sig plus R1 parallel to R2. So let me draw and show it to you instead of doing that. So let me draw this. So here I have R sig. Here I have R1 parallel to R2, which is nothing but Ri. This is your R sig. Here I have Vs, and I mean, here is my V in, I mean, plus minus, right? Here you can easily write plus minus, and here also we have plus minus. Now, how can we write? We can simply apply a voltage division rule, right? So by voltage division rule, what is the value of V in? So V in will be equal to R1 parallel to R2 divided by R1 parallel to R2 plus R sig, multiplied by Vs. Now instead of multiplying, we'll divide it. Okay. So this is the value of V in upon Vs. Okay. Or you can also write it as Ri divided by Ri plus R sig. So that's the value of V in upon Vs. Let me mark it with yellow color. Okay, fine. So we calculated the quantity V in upon Vs over here. Okay, now let us concentrate and find out what will be a gain of the second stage and gain of the first stage. So let me start with the second stage gain. Always start with the second stage gain. So we'll go over here and see the second stage now, right? And let me use orange color, right? Now, what is V out? If you see carefully, what is V out? So V out will be these three resistances in series, in parallel, right? So I can write over here, V out is nothing but these three resistances in parallel. And what is this current? This current is nothing but IC, which is nothing but GM2 into V pi, correct? So I can, and it's outgoing current, it's not flowing into the ground, right? So I can write V out is equal to minus IC into the parallel combination of these three resistance, which is nothing but R out only, right? So V out is equal to minus IC into R out, right? So this is the hint which we will follow. And also what else we can write? We can also write that your and IC is nothing but GM2 into V pi. And what is V pi over here? What is V pi from here? V pi, if you see carefully, it is same as V1. They are in parallel, right? It's a clear, distinction over here that V pi is in parallel with V1. Now, let me write the formula for this again down. So we were concentrating on finding out the value of expression for AV2. So we got V out is equal to minus IC into R out, right? Now let us elaborate that now. What was the value of IC? So IC collector current was GM2 into V pi. And what was the value of R out? R out was nothing but RO2 parallel to RC parallel to RL, right? And also what was the value of V pi? V pi was equal to V1, correct? So let me rewrite the value of V out. So V out is equal to minus GM2. Instead of V pi, we'll write V1 into R out, which is RO2 parallel to RC parallel to RL. Now, actually, we want V out upon V1 only, right? Because that is your AV2, V out upon V1. So over here, we will write AV2, which is nothing but V out upon V1 is equal to minus GM2 into RO2 parallel to RC parallel to RL, right? So this is the formula for the voltage gain of the second stage, right? So this is the expression. Okay, let me mark with highlight with yellow color. Yeah, this is the gain of the second stage. AV2, let me write over here. This is the voltage gain of second stage. Okay, now we are only left out to calculate the voltage gain of the first stage. So what will be the voltage gain of the first stage? Let us check it out. So let's come at the first stage over here. Let me again use orange color. Right. So now, what is the value of V1? V1. What is the value of V1? V1 will be, let me mark over here. This is your ID, current ID. Current ID, V1 will be, current ID is outgoing current. That means it's not going towards the ground. So it will be, V1 will be minus ID into resistance. Now, what all resistance do you see over here? RO1, RD, they're all in parallel. RO1, RD, then we'll have R3 parallel to R4, then we'll have R pi. So these many resistances in parallel which we will have over here. So V1 will be I minus ID into RO1 parallel to RD, parallel to R3, parallel to R4, parallel to R pi. Okay. And what is the value of ID? ID is nothing but GM1 into VGS. And what's the value of VGS over here? So your VGS is nothing but equal to V in. Your VGS is equal to V in because they are parallel. So VGS over here and V in are same. So let me rewrite this down below over here. So let me go down, and now we will concentrate on calculating AV1, gain of the first stage. So for calculating AV1, we are concentrating on V1. And what did we write for V1? Minus ID into RO1 parallel to RD, parallel to R3, parallel to R4, parallel to R5, right? And what was the value of ID? ID was GM1 into VGS1. And what was the value of VGS1? VGS is nothing but Vn. Now let me let me rephrase the formula expression of V1. So that is V1 will be equal to minus of GM1 into VGS, where VGS is V in. So GM1 into V in into these 5 resistances are in parallel: RO1, RD, R3, and R4 and R pi, right? And now we know what is the formula for AV1. AV1 is V1 upon V in, right? So, okay, sorry. So over here, what is V1 upon V in? V1 upon V in. So that is AV1, which is V1 upon V in, is equal to minus of GM1 into RO1 parallel to RD, parallel to R3, parallel to R4, and parallel to R pi. So this is the expression for the voltage gain of the first stage. Okay, let me mark it with yellow color. So, and let me also write the voltage gain of the first stage. So remember, don't by heart this formula. We can easily draw the mid-frequency model and write down eventually these formulas by observation also. Okay, so don't derive this again and again. You have to, practice it. Looking at the cascade amplifier, you can directly write it down, right? So this is, let me write over here. This is the gain of first stage. Okay, this is the gain of the first stage. So what is the overall voltage gain now? Now that we have the expression of AV1 and AV2, so total gain, or we can write it as AVT, will be equal to AV1 into AV2 into Ri upon Ri plus Rsig. Okay, where Ri was, what was the value of Ri? Ri was equal to R1 parallel to R3, right? So this is the overall expression for the voltage gain. Voltage gain for the given amplifier, right? I think we have completed the required topic. We have estimated the voltage gain, input resistance, and output resistance for the given common source, common emitter, cascade amplifier. Okay. Now let's look into a little bit of advantages. Now we have, so far we have studied. Let me just write it little bit. Yeah. So let us comparatively understand what are the features of every configuration, right? So let me use a blue color over here, right? So first we started common emitter, cascade. Then we did common source, cascade amplifier, and now we did common source, common emitter. So why not it is common emitter, common source, right? There is a reason for it, right? So let us discuss this in detail about the comparison of all the three configurations. Yeah. So first of all, let us compare from the point of view of voltage gain. So voltage gain of common emitter is the highest. Okay. The voltage gain of common emitter is the highest, and any value greater than around 1200 or 1500 will be sufficing for the highest gain. Now, in case of common source, the voltage gain is the lowest, right? So any value which is less than around 150 or 200 will be considered as a voltage gain for the common source amplifier. Now in case of common source common emitter, the voltage gain is moderate, not very high or not very low, and it will be in the range of anything greater than 500 and less than, let's say, 1200 or 1000. Okay, so a voltage gain in the range of 500 to 1000 will be the voltage gain for the common source common emitter amplifier. Now let's look at the input resistance. So how about the input resistance R in? Here it is lowest. For common source common emitter configuration, the input resistance is nothing but the input resistance of the first stage, which is common emitter, and common emitter input resistance is very low because of R pi. Now in this case, our CS amplifier, CSCS, we have common source, right? And common source uses a MOSFET, and MOSFET internal input resistance is very, very high. So here it is highest, and over here also it is highest. In case of third case, it is also highest. Now why it is also high? Because you see, in case of a voltage amplifier, right, we are all building up a voltage amplifier, right, cascade amplifier. Why do we cascade stages? So that we get a gain greater than 1000. And why do we connect common source first? We connect the common source first in the common source common emitter. The reason being is that common source will provide high Rn if we connect it first. If we connect common emitter first, then it will provide a low input resistance, which is bad for a voltage amplifier. That's why common source in common source common emitter, common source is connected first, right? So yeah, that is the brief comparison of all the three configurations which we have studied so far, right? Now, yeah, so we have completed the desired topic, that is we have analyzed the common source common emitter RC coupled cascade amplifier. By the way, where it is RC coupled, this value, this capacitor over here, and where is the resistor? Resistor is nothing but the input resistance of the next stage, which is R pi in parallel to R3 in parallel to R4. So they will form the RC coupling. And what's the advantages of RC coupling? The Q point of the first stage, which is your common source amplifier stage, and the Q point of the common emitter amplifier stage will be isolated from each other. So that's the advantage of RC coupling. Okay, so yeah, so we have come to the end of this session. I hope that you all have understood the analysis and you all will practice this in your books on your own. So draw the circuit diagram and analyze it and derive those formulas on your own. That in that way you will gain confidence. Okay, so yeah, other than that, that is all for today. Thank you all for joining. Next time we'll solve a numerical on common source common emitter RC coupled cascade amplifier. So until then, have a good day and thank you.